Today's topic is linear and angular velocity, and this is a topic that a lot of the times people have a difficult time with. And I'm not sure why, because the formula that relates the two is pretty straightforward, but nonetheless, people struggle with it. So just keep that in mind as we go through it. Let's see if we can get it right the first time. So when we talk linear velocity, this you're pretty comfortable with, I'm most certain with. Miles per hour, feet per second, these are things we talk about on a daily basis. Angular velocity, we don't talk about that much. What we're talking about, how often you rotate or how many times you rotate over a period of time. So this is kind of like a round in a circle. Thus our study with circles and trig. So we're talking about degrees per second, revolutions per minute, RPM, we're used to seeing, et cetera, et cetera, et cetera. All right. Now, the formula that relates these two is the linear velocity, which is in miles per hour, is equal to a radius multiplied by your angular velocity, how many times you spin around for a period of time. But this is really important. Your angular velocity has to be in radians per period of time. And both the measures that we see above are not in radians. They're in revolutions or degrees, what have you. And the thing you probably need to know is one revolution around in a circle is equal to how many radians? 2 pi. And radians is like a unit that's not really a unit. It never really appears, but we know that the radian value of one revolution, the degree value is 360, but the radian value is 2 pi. So let's start with our problems. We want to determine the angular displacement, which is another word for how many angles have been covered or how many degrees have been covered or radians covered in 2 revolutions. So if I have 2 revs, and as we just stated, we can do a little dimensional analysis. 1 rev is equal to 2 pi radians. Then I do my multiplication, my units cross out, and I'm left with 4 pi radians. All right, and we want to determine the angular displacement, how far around we've gone in radians for 3.8 revolutions. So again, 3.8, even though it's not an even number, revs, we do our dimensional analysis. 2 pi radians is equal to 1 rev. Again, the units go, and we're left with, what, 7.6 pi radians. Pretty straightforward. It's just a dimensional analysis calculation. Now, we want to determine the angular velocity, which is radians over a period of time. So what we have is 40 revs in 3 seconds. And we want to talk about how many radians in 1 second for this example, okay? So in this case, we need to convert our revolutions to radians once again. And we know 1 rev equals 2 pi radians. And we'll do that multiplication. We get 80 pi over 3 radians per second. And if we would want to convert that using decimal, we can certainly do that. Converting, we get roughly 83.77 radians per second. Now in this next example, what we're going to want to do is have radians per minute because we're talking about minutes. So if I have 2,700 revolutions per 4 minutes, I want to know how many radians in every minute. So once again, 2 pi radians, 1 rev, those units go. We're left with 5,400 pi radians That's 5,400 over 4 pi radians per minute. And again, I can convert that by doing the calculations. And that gets me approximately 4,241.15 radians per minute. All right, let's move on. And here's where we start struggling, word problems. So I've got a Ferris wheel, and it's got a 60-foot diameter. So here's your Ferris wheel. Diameter 60 feet. I know in this I'm going to need my radius, which is 30 feet. And it makes one revolution every 2 minutes. Let's just put this M in here since I screwed that up. And we want to know what is the speed of a seat on the edge of the wheel. Well, as this thing rotates, let's say it rotates this way, and some guy's sitting in a chair up here, it has a linear speed. And when we're talking speed, we're talking linear, even though they won't say it. All right? So we know that the linear velocity is equal to the radius times my angular velocity. So what I need to do is find my angular velocity first. Here's my angular velocity, or my angular displacement, whatever you want to call it, okay, in revolutions per minute. All right, but what I want to do is I want to take and convert that to radians per minute. So again, 1 rev equals 2 pi radians. And I end up with the 2's reducing. That gives me pi radians per minute. And that's my angular velocity. So now to find my linear velocity, I take my radius, which is 30 feet, multiply that by pi radians per minute. And here's where that whole idea of radians being a unit but not a unit, when I multiply these together, I get 30 pi. The radians go away, feet per minute. Why does it go away? Because radians aren't really a unit. It's just kind of like a label. So I get 30 pi feet per minute. All right, and if I wanted to convert that again, I just take 30, multiply it by pi, and get about 94.2 feet per minute. So that's how fast you'd be moving in a seat on that Ferris wheel. Again, all we're using is this equation, and we'll be using it all day long. Let's do another one. Now, we've got a pulley with a radius of 20. So the radius here is 20. And it turns at 6 revolutions per second. So the 6 revolutions per second is my angular velocity. We want to know the linear velocity of a cord driving the pulley. So this cord's pulling this round circle. Well, here's the deal. Anything that's straight is a linear velocity. So this cord has a linear velocity. All right, the circle has an angular velocity. Anything coming off on a straight line from that circle becomes linear. So here we go. I've got 20 centimeters for my radius, and I have 6 revs per second. But I'm going to convert that to radians. 1 rev, 2 pi radians. Once again, seems to be the same process over and over. So I get 12 pi radians per second. And we want to find the linear velocity in meters per second. So what I need to do is I need to take and convert the 20 centimeters into meters. Again, dimensional analysis. So If I want meters, I got to put that on top. 1 meter equals 100 centimeters. Therefore, these reduce to what, 1/5 or 0.2 meters for my radius. So now my linear velocity equals my radius, which is 0.2 meters, times my angular velocity, which is 12 pi radians per second. Multiplying those together, I get 0.2 times 12, which is going to be 2.4 pi meters per second. And again, if I wanted to multiply the 2.4 pi out, I could do that, but that's probably good enough. We'll leave it. All right, next example. So this is a little more difficult problem. It involves 2 pulleys and a belt connecting those pulleys. Now, the belt in this portion is straight. So at this point here and this point here, we're going to have linear velocities. This wheel spins in a circle, and this wheel spins in a circle. So they're going to have angular velocities. Now, if you think about it, if I were to put these 2 wheels on the ground and spin them at the same time, the smaller wheel would actually go through more revolutions in the same time as the bigger wheel if I put them next to each other and they cover the same distance. So the smaller wheel's always going to have a faster angular velocity than the bigger wheel. It's just going to spin faster. It makes sense. The belt that connects both of them is going to be moving at the same speed all the time. So its linear velocity at each wheel is going to be the same. Let's go through this problem now. Angular velocity of the large wheel, I'll put ang L, is equal to 100 RPM. So that's revs per minute. And then we want to find the angular velocity of the smaller one. Well, in order to do that, to find the angular velocity of the small, that multiplied by the radius is going to equal the linear velocity of the small. But here's the deal. The linear velocity of the small, as we already stated, equals the linear velocity of the big, because the same belt is traveling off each of them, and that belt is in a straight line in both cases. All right, so let's find the linear velocity of the big wheel. All right, and I'll change that L to B, call it big. All right, so the linear velocity of the big wheel is equal to the radius of the big wheel, which we know is 8 centimeters. That's going to be multiplied by the angular velocity of the big wheel. Well, we've got a problem because this angular velocity isn't in radians. So let's go angular velocity big is equal to 100 revs per minute. And I know 1 rev is 2 pi radians. So I get 200 pi radians per minute. And that's my angular velocity. We're going to put that here. My linear velocity then of the big, multiplying these together, is 1600 pi centimeters per minute. And if I want to find the linear velocity of the small, I take my radius of the small, multiply it by my angular velocity of the small, and get my linear velocity. but I know that the linear velocity of the big is equal to the linear velocity of the small. So I'm going to make a substitution now in this formula. So let's do that. Let's say 1600 now, pi centimeters per minute is equal to my angular velocity of the small times the radius of the small. And going back to our problem, we know the radius of the small is 3 centimeters. So I'll put that in, 3 centimeters. Divide both sides by 3, and I get 1600 pi over 3. The centimeters reduce, leaving me with radians per minute is my angular velocity of the small. Now, in most cases, they're going to want us to put this in RPMs. So if we're going to put it in RPMs, we have to convert back once again. I know that I have 1600 pi over 3 radians per minute. And I know that 2 pi radians equals 1 revolution. So we're just doing this dimensional analysis backwards now. The pi's are going to reduce. The 1600 and the 2 reduces to an 800 over 3 revolutions per minute. And we're done. So let's do another example. Or I think actually, let's not do another example. Let's answer some questions. So here are some questions for you to answer today. And we'll see you tomorrow.